Good evening, ladies and gentlemen. Welcome to the show. We are airing from Sofia Tech Park. Thank you for being with us. Today, we will have a very interesting discussion on a very, very peculiar scientific topic that most of you are probably not very aware of. But as you will probably find out, it's one of the most important developments in science for maybe the last 100 years. So the first direct detection of gravitational waves from the merger of two massive black holes, more than 1 billion light years away from the Earth, became a global media phenomenon when it was announced in February 2016. Now, this remarkable discovery was made by two giant interferometers known as advanced LIGO, which are the most sensitive scientific instruments ever built. It first vindicated Albert Einstein's general theory of relativity and has been widely hailed as one of the greatest scientific breakthroughs of the century. Now, today, what is the LIGO experiment? What is the nature of gravitational waves and how it will change the field of physics and our understanding of the nature of the universe? Today, we speak with Martin Hendry, who is a professor of gravitational astrophysics and cosmology at the University of Glasgow, where he is currently also head of school. His main research interests are in the analysis of astronomical surveys, including the development of optimal methods for multi-messenger astronomy, combining data from both electromagnetic telescopes and gravitational wave observatories. Martin is a senior member of the LIGO scientific collaboration, for which he currently chairs the LSC Communication and Educational Division and the LISA Consortium. Martin, are you with us? Can you hear me?
Hello there, Petko. It's a real pleasure to be with you.
Yeah. Hi, good evening, sir. I hope you are in a good health and in a good mood because there are difficult 40 minutes ahead of us where you are going to explain a pretty complex phenomenon, a pretty complex science. But I'm sure that you're the right person to present it in a way that would be most understandable for me and for the layperson as well. So whenever you're ready, Martin, you can go ahead.
Thank you. Well, I'm delighted to have the opportunity to share with everyone the story of this remarkable discovery that you briefly mentioned the timeline for in your opening remarks. It is indeed just about 5 years since we announced this remarkable discovery, and I was a major part of the planning for that announcement. It was probably the busiest period of my life, but nonetheless, what I really want to share with you is that this was not the end of the story. It was really just the beginning. And I'm going to fill you in on firstly how we made that detection, but what's been happening since and what the future holds in store. So I've called this presentation Listening to Einstein's Universe, and I will try to make it fairly short so that there is lots of time for questions. I look forward to hearing those questions a little later. You talked a bit about who I am already, so let me just mention a few more words about what gravitational astrophysics and cosmology really are. It sounds a very grand title, and essentially it's about understanding some of the big questions on the origin and the evolution of our universe. How did our universe begin? Why is it expanding? What might happen to our universe in the future? And for about 15 years, I've been working in this new field of gravitational wave astronomy, where we're studying the universe in its most extreme conditions, where we have violent cosmic events like black holes and neutron stars, and the gravitational waves that are produced, well, as you said, many people say that their detection is one of the biggest scientific breakthroughs of the century. So that's what I'm going to try to share with you this evening. And I'm speaking on behalf of the LIGO scientific collaboration, not formally, but I hope to represent something of the spirit of that collaboration, the fact that it involves scientists from so many countries, as you can see, across the world and indeed across Europe, in our partner collaboration known as Virgo. And we are also now partners with Kagra, which is a detector in Japan. So more on that towards the end of my talk. But even within just the LIGO collaboration, there is well over 1,000 scientists and engineers contributing to this effort. So I want to really just pay tribute to the combined efforts of this huge family of scientists who are pioneering this new field of gravitational wave astronomy. So what the main theme of my presentation is the picture of gravity that we have from Albert Einstein. Just over 100 years ago, as you mentioned, Petko, Albert Einstein developed his general theory of relativity. And this was a radical rethinking of what gravity means. Several hundred years before, Isaac Newton had developed the idea of gravity as a force between every massive body in the universe. And frankly, Newton's picture of gravity gets us a very long way. We can use the equations that Newton developed to understand why a plane would fly through the sky, why a spacecraft could travel from the Earth to the moon, why the Earth orbits the sun, why the sun orbits within our galaxy. But Einstein, towards the beginning of the 20th century, began to realize that there were some issues with Newton's picture of gravity. Some rather deep, almost philosophical issues about how this force gets from one point in space to another. And he developed a radical new way of thinking about gravity, not as a force between massive objects, but instead as a curving of space and time themselves. So a little bit after Einstein published these theories, one of his fellow scientists, John Wheeler, came up with this phrase that is on the screen now. John Wheeler described the essence of general relativity as follows. It's that space-time tells matter how to move, and matter tells space-time how to curve. So what on earth does that mean? Well, frankly, to really understand in detail, we need lots of maths, and I'm not going to present that this evening. You'll be relieved to hear. But let's try to use a familiar analogy. Well, familiar to me, but maybe familiar to some of you also. We can think of space-time like a stretched sheet of rubber, like a giant trampoline. And if we imagine dropping a planet like the Earth on such a trampoline, the trampoline will bend. And it means that the straight lines which delineate the surface of the rubber sheet will no longer be straight. And the idea here is that the presence of matter in the form of the planet is shaping the space-time around it. Matter is telling space-time how to curve, and then that space-time curvature tells other bits of matter like the moon, or even actually not just matter, but rays of light passing close to a massive body to follow that curved path. So we have this picture of space-time as a changing, curving substance almost, resulting from the presence of matter and energy in the universe. And this analogy, it's not perfect, but it gives us this vivid way of thinking about how other objects, or as I said, even light, will travel as they traverse the universe and follow these natural contours of curved space-time. Now, for most of the 20th century, we saw some dramatic developments in astronomy, especially in the second half of the 20th century, as we began to open up new windows beyond the visible light that our eyes can see. So all of the forms of light we refer to as electromagnetic radiation, and it goes all the way from gamma rays to radio waves. I noticed that one of your presentations in February is about the radio universe, and there have been remarkable discoveries made by improving our radio telescopes in recent years. But Einstein's general relativity predicts a whole new window in the cosmos beyond electromagnetic radiation, and that's what we call gravitational waves. So gravitational waves are to do with that space-time curvature, but they're produced when that space-time curvature changes. And I think you're going to play the video on your side, because the one on my screen is maybe a little unstable with the internet connection. Yes, I can see it playing more smoothly now. And what we're seeing here is a cartoon of two stars orbiting each other very, very close together. And what general relativity says is that that situation can shake space-time so much that it sends waves spreading out through the universe. These are the gravitational waves that LIGO and Virgo have been searching for. So how do we detect these cosmic ripples produced by changing gravitational fields? Well, the challenge is that, like ripples spreading on a pond, those waves become weaker as they spread out through the universe. And by the time they reach us, they disturb our patch of space-time by a really incredibly tiny amount. So to detect them, we need to be able to detect movements in our patch of space-time equivalent to less than 1,000th the size of a proton, the subatomic particle that you find in the nucleus of an atom. Or perhaps a better way to visualize these incredibly small sizes is to think of a hair on your head. We are trying to measure 1 millionth the width of that human hair. So this is why the LIGO detectors really are the most sensitive scientific instruments ever built. So what do they represent and how do they work? Well, LIGO stands for Laser Interferometer Gravitational Wave Observatory. And these are very large instruments. They are L-shaped. You can see the two detectors in the US. One is in Louisiana, the other is in Washington State. They are separated by 3,000 kilometers. And the arms of the detector are 4 kilometers long. So inside those arms, there is a nearly perfect vacuum. And I think you'll play the video smoothly on your side, because again, let's not have it jerking. And that video is showing us just a brief journey above the two detectors in the US. Let's watch it one more time. First, we are seeing LIGO Hanford in Washington, and then LIGO Livingston in Louisiana. So these are huge scale facilities. And as I said, inside those arms, what we have is a near perfect vacuum. And that's crucial because in that vacuum, we have laser beams traveling along the arms and bouncing off mirrors at the ends of the arms. And the laser interferometer part of LIGO's name is revealing to us the basic principle of how LIGO works. It's interferometry. So what does that mean? It means that we are looking for the interference pattern when the laser beams bounce off those mirrors and then return to a central mirror and are recombined. And if a gravitational wave were to pass by the Earth, it would produce an effect that squeezes and stretches the fabric of space-time by an incredibly small amount, as we said, 1 millionth the width of a human hair. But that would produce the pattern that we see in the cartoon on the right. We see that squeezing and stretching. So one arm is longer, the other arm is shorter, but by this tiny amount. And that will mean that the two laser beams are no longer in step with each other. That's what we call when they interfere with each other. So we are looking for an interference pattern caused by changes in the length of the arms, but changes which are unbelievably tiny, equivalent to the width of a hair over the distance from the Earth to Alpha Centauri, the nearest star beyond the sun, or equivalently 1 millionth of the width of one of those hairs. So that presents an enormous engineering and technological challenge. And this is a very complicated looking graph, but all you really need to take from it is that the sensitivity of these detectors is limited by many other factors. The squeezing and stretching of space-time that we are trying to measure is coming from a passing gravitational wave. But many other phenomena can change the length of the arms and the length of the path traveled by the laser beams. So they are listed there, and I won't go into the details, but they involve effects to do with the detectors themselves. or effects to do with the external environment at the two LIGO locations. So what we need to do is to try to isolate our detectors as best we can from all of those local disturbances. And we'll describe in a moment how that is done, but you cannot do it perfectly over all frequencies of gravitational waves. So what we find is our detectors are most sensitive to gravitational waves with a frequency of a few hundred hertz. That's a few hundred cycles per second. But outside of that range, the noise from the local environment and from the detectors is too large, and we cannot detect gravitational waves with any sensitivity. So to give some perspective on how all of that works, let's think of what type of signal we might expect to observe. If, for example, we have two black holes colliding, then as they spiral in towards each other, the gravitational wave disturbance they produce will become stronger and stronger until the black holes merge, and then space-time will shake some more and it will then settle down. So the pattern you see in the graph is showing exactly that. And this is the prediction from Einstein's theory of what the gravitational wave signal should be like. It should involve an increasing frequency, an increasing strength or amplitude, and then a decrease after the two black holes merge. So it really helps us a lot in trying to detect these signals that we know what we are looking for. And I think a good analogy here is to imagine listening to a conversation in a noisy lunchroom. In the days of COVID, this scene would be, well, almost impossible, I suppose. But in a busy high school like this, you would have conversations going on at each table where the students are talking to their friends, but the background noise is almost deafening. But I'm sure if they know roughly what their friends are talking about, then they can hear those quiet conversations even with all the background noise. And that's the challenge that we face detecting gravitational waves. The signals are very quiet. The background noise is very loud. So what we want to do is to reduce as much as we possibly can the background noise. So the detectors operated during the early years of the 21st century, but they were not yet sensitive enough. There was too much background noise to hear the signals from the cosmos. But then in 2010, there was some improvements made to the detectors to improve their sensitivity and to make them less vulnerable to those background noises that would swamp any possible signals. So what was done was to replace the steel wires that suspended the mirrors at the end of the arms and replace those with glass fibers, incredibly delicate and very much less vulnerable to shaking because of seismic noise and other sources of disturbance in the local environment. And then in 2015, we were ready to begin listening to the universe. And this is what we heard. So let me pause the video. I was playing that several times. In fact, the real signal only lasted a fraction of a second. So I was repeating the signal multiple times. And I was doing one other thing to help it be more audible. I was playing the signal at a higher frequency. Gravitational waves are not sound waves, but we can render them as sound waves to make it easier, perhaps, to understand them. Because in fact, that pattern that we see sounds like a chirp, a little like the chirping sound of a bird, rising in frequency, rising in loudness, and then fading away. So that's what we saw, or if you like, heard in September 2015. And the remarkable thing about this very first signal was the similarity of the two patterns seen in LIGO Hanford and LIGO Livingston, even though the detectors are 3,000 kilometers apart. So that immediately gave us great confidence that we genuinely were detecting a signal from out there and just some local disturbance mimicking the type of signal we expected. So in fact, what we think we were seeing, what our painstaking analysis revealed over the 5 months that followed, was something like you see in this animation. So we had two black holes orbiting each other, spiraling in towards each other, shaking space-time violently as they did so. And just at the moment when the black holes merged, the burst of gravitational waves released, shown in the cartoon as a red spike. That is the signal that LIGO detected. So between September 2015 and February 2016, we worked round the clock trying to ensure that we had made a genuine detection, that we had not messed up, and also trying to work out the properties of these black holes. What exactly is a black hole? Maybe many of you have some idea already, but I should briefly mention that. A black hole is a star which is so dense and so massive that its gravitational curvature, the curving of the gravitational field, because of that mass, remember the slide of the trampoline, that curvature is so strong that even light can escape. That's why we call them holes, because light does not escape from inside what's called the event horizon of the black hole. So as we played the animation, we are seeing the event horizons of the two separate black holes merge and become one. And the gravitational waves emitted during that process are represented in the animation by the ripples spreading out from that merger. So by analyzing the form of the gravitational wave signal, we were able to work out a lot about those black holes. We were able to deduce that the two black holes had masses of about 30 times the mass of our sun. More precisely, we estimated that one was about 29 times the mass of our sun, and the other one was 36 times the mass of our sun. If you add those two together, you get 65 times the mass of the sun. But by analyzing the final part of our waveform, we could also estimate the mass of the black hole that was left behind. And that had a mass of only, it's still a big number, but it was 62 times the mass of our sun. So in the merger, the equivalent of 3 times the mass of our sun was released in the form of gravitational wave energy. And that was released in such a dramatic circumstance that it was equivalent to the luminosity of every star in every galaxy in the entire universe. So it's no wonder that this discovery was such a big deal. And in 2017, it was awarded the Nobel Prize for Physics to 3 senior members of the LIGO scientific collaboration. So by detecting gravitational waves, we're tapping in to the immense energy locked up in the curvature of space-time. But as I said at the beginning, this was not the end of the story. It was just the start. And in August 2017, just a few months before the award of the Nobel Prize, a third detector joined our network. This is Advanced Virgo, close to Pisa in Italy. And with all 3 detectors, we have the opportunity to determine the position from where the gravitational waves come much more precisely. For any 2 detectors, we can try to localize the direction from where the gravitational waves come by timing when they arrive at the 2 detectors. There will be a short delay between them arriving at one, let's say LIGO Hanford, compared with LIGO Livingston. And then there is a ring on the sky which shows all the positions where the source could have come from and would have produced that short time delay. So that would be the red ring on my diagram here. But as soon as you introduce a third detector, you can consider 3 different pairs. And that gives us 3 rings on the sky, and the true source location is where they overlap. So this gave us the ability to determine the sky position much more precisely. And that paid off very quickly. The Virgo detector began operating on August 1st, 2017, and just 2 weeks later, we observed another pair of black holes merging, but with much better pinpointing on the sky, to about 60 square degrees, compared with some of the earlier events, which were hundreds of square degrees on the sky. And then just 3 days later, something else quite remarkable happened. I'm hoping I remember to share my sound. And what hopefully you are hearing is the chirp sound of the gravitational waves. Perhaps we'll play it one more time. So we hear that rise in frequency, but then just 1.7 seconds later, you hear the ping, which is the arrival of gamma rays. So what was amazing about this event is that we didn't just detect gravitational waves, we also detected radiation across the electromagnetic spectrum. So this was coming from not 2 black holes merging, but we believe 2 neutron stars merging. Neutron stars are almost as weird as black holes. They are the remnants of massive stars, which are perhaps only 15 kilometers across, but they have a mass greater than our sun. So 1 cubic centimeter would weigh about 1 billion tons. And when 2 neutron stars collide, it had long been expected that this could produce not just a strong gravitational wave signal, but a strong signal in gamma rays, in X-rays, in fact, across the whole electromagnetic spectrum. And this is precisely what we saw, because on August 17th, we were able to identify the sky position so precisely that optical telescopes could identify which galaxy the gravitational waves had come from. And that allowed us to measure not just the distance, but what we call the redshift. I can discuss that later in the questions. And measuring distances and redshifts is what Edwin Hubble and Georges Lemaitre helped us to understand in the early 20th century to explain the expansion of the universe. So that's one of the things we can now do with gravitational waves as a useful alternative to doing it with light. And our measurement of the expansion rate of the universe is shown in this graph here. It's quite broad. Scientists love to draw graphs, and this one is really just telling us that we can do this in principle. And the answer we got agrees well with previous determinations using light. Those are represented by the vertical green and orange bands. But notice the green and orange bands don't agree with each other. So measuring the expansion of the universe using light is currently rather controversial because different methods give different answers. Now, we were the ultimate diplomats because our gravitational wave answer is so imprecise that it agrees with both the green and the orange. But of course, that will improve. In the future, as we make more of these measurements, we will be able to refine our prediction for the expansion of the universe much more precisely. And perhaps we can help to settle this debate over which is the correct value. Another consequence of our detection was that optical telescopes could study the aftermath of the neutron star collision, and it revealed the presence of what's called a kilonova, the remnant where the environment was so extreme that it seems a likely location for the formation of the heaviest chemical elements like gold and silver and platinum. So this confirms the widely held belief that merging neutron stars are indeed where most of those precious metals are manufactured in our universe. So this brings us to almost the present day. In December 2018, we published a catalogue of all the detections that we had made until that point. 10 pairs of black holes merging, plus the neutron star pair that we have just been discussing. But we didn't stop there. Firstly, we've spent a lot of time analysing those data. Now, I won't describe this slide, it's rather complicated, but if you want to hear more about that, I will happily discuss it in the questions. Basically, we don't just want to validate Einstein's theory, we want to test it. We really want to test it to the limit. And so far, Einstein's theory has passed the test, so Einstein is fairly happy. But I can discuss in a little more detail, if you wish, some of the tests that we have carried out. And then the next big development was upgrading and improving our detectors even more to make them even more sensitive so that we could probe deeper into the universe and observe more gravitational wave events. So this was our third observing run, and that began on April 1st, 2019. It ran for approximately 1 year. We had to finish early because of COVID. But during that third observing run, we did things differently. When we had a candidate gravitational wave event, we announced it publicly immediately because we wanted to give astronomers the best possible chance to go and look for electromagnetic counterparts, like we saw so successfully in August 2017. And in fact, members of the public could also follow these alerts. We created an app called Chirp. You can download it from Google or from Apple, and that would buzz or chirp when a candidate gravitational wave event was detected by LIGO and Virgo. So our third observing run was terminated in March of 2020. And we divided it into two parts, the first 6 months and the second roughly 5 months. So O3A and O3B together gave us dozens more candidate gravitational wave events. And very recently, we've announced some confirmed detections from that third observing run. So here are some of those presented kind of montage. There was, for example, an event that we announced in January of last year, which was another pair of neutron stars colliding. But this time it was more distant, and we weren't so lucky to observe the gamma rays or the X-rays or the kilonova or all of that. But we're still very confident that it was a pair of neutron stars. And this is an artist's imagining of what that merger might have looked like. So it emphasizes that in 2017, we got extremely lucky because that first neutron star collision was close enough to us that it could be observed with all of those other telescopes. We won't always be so lucky, but there are many astronomers searching the skies to try to spot those electromagnetic signals. The next one we announced in 2020 was this one up here, and this one has a little animation. This was two black holes where the black holes did not have the same mass. They weren't even similar in mass. One was about 3 times heavier than the other. And that changes the pattern of gravitational waves in interesting ways. It's a little bit like having harmonics on a musical note. Instead of it being a pure single frequency, you have lots of frequencies mixed together. And that gives more structure, which makes our music more interesting, but also for gravitational waves, makes the science we can do more interesting, more deep, more compelling. And then in June of last year, we announced another pair of compact objects that collided, and that one was also rather lopsided. One was about 10 times more massive than the other. It's up here in the corner. And in that case, the lighter companion, we don't know whether it was a neutron star or a black hole. It was either the most massive neutron star we've observed, or the least massive black hole. So it's opened many questions about how these compact objects form and how we might learn more in the future. And then the final exceptional event that we announced was in October. And it was of the two most massive black holes that we have observed colliding yet. It was 1905-21. The event was detected the previous May 21st. And it's an example of what we call an intermediate mass black hole. We know about even more massive black holes, but we just haven't seen them collide yet. But possibly collisions like this one perhaps are part of the story of how those really massive black holes build up. And I'll talk more about that in just a couple of minutes at the very end of my presentation. The final piece of news from LIGO and Virgo is about the release of our new catalogue. So the 4 exceptional events that I briefly mentioned there are part of a total of 50 events that we've observed since gravitational wave detections began. And that's up to the end of October 2019, including therefore the first half of the third observing run. So we can see the dramatic increase in the number of confirmed detections because we've made the detectors more sensitive. So here's one way to represent all of those detections. The blue is showing all the black hole pairs that we've seen, but we know about some black holes from electromagnetic radiation. They're shown in purple. So now what you see is that we are observing many more black holes in gravitational waves than we observe in a similar range of masses using light. That's because we can't see a black hole in light at all, but we can infer that it's there from the effect it has on its surrounding environment. But with gravitational waves, we don't care about that. We can detect the gravitational waves directly from the black holes. And here is our little animation of all of those black hole pairs merging together. Of course, they're shown in blue because if I showed them in black, you wouldn't see them on the screen. But this gives us some sense of the rich variety now that we have in our population. And that's really where the focus is now shifting. Yes, we are interested in individual events, but we're also interested in learning things about our universe from studying the population of those events. So coming soon will be the confirmed detections from the second part of the third observing run. So we hope to have that completed by the middle of this year. And then in 2022, we will begin another observing run with even more sensitivity, and also with the Japanese detector KAGRA joining our observations. Now, the more detectors you have, the better you can localize on the sky the position of the gravitational waves. So adding KAGRA to Virgo and LIGO Hanford and LIGO Livingston will already improve things. There's another detector in Germany called GEO 600, but it's not so sensitive. LIGO India is the next sensitive detector after KAGRA, and that should be coming towards the end of this decade. So there are many exciting developments ahead. Here is an artist's impression of the LIGO India site. The basic design will be the same as LIGO Hanford and LIGO Livingston, but because it's on the other side of the world, that will greatly enhance our ability to localize the sources on the sky. And the sensitivity of the detector will also be improved. Remember that complicated curve with the dip in the middle, the sweet spot around a few hundred hertz? Well, the upgrade to Advanced LIGO that we call Advanced LIGO Plus, that will be completed on a similar timescale to the introduction of LIGO India, which will also be at that enhanced sensitivity. So that will allow us to observe many more events deeper into the universe. Now, I'm almost done. This slide just emphasizes how much better we can localize when we have multiple detectors. So what you need to look at is how small these little shapes are when you have 5 detectors compared with only 4. So already with 3 detectors, things are better, but with 4 and then 5, they will continue to improve as we add more detectors to the network. And we also want to build even more sensitive detectors that will take us into the 2030s. So plans are being developed for those that will observe much deeper into the universe to see things essentially that happened a long time ago in a galaxy far, far away. And those plans, well, there's a project led by Europe called the Einstein Telescope, and there's another one led by the US called Cosmic Explorer. And both of them will be around 10 times more sensitive than Advanced LIGO Plus, which means they will be sensitive to a volume of the universe about 1,000 times greater. So we can fully expect to be detecting gravitational waves almost every hour, certainly multiple times per day, by the time we reach these third generation instruments. But the very final topic I want to mention is extending the gravitational wave spectrum beyond the visible, if you like, to other regions. So we don't see gravitational waves, but if we draw the analogy with electromagnetic radiation, for a long time, the only window we had was visible light. That's like the only window we have in gravitational waves is ground-based interferometers. And then in the 20th century, we went far beyond the visible to include radio telescopes, gamma ray telescopes, X-ray telescopes, and so on. So we want to do the same in gravitational waves. And there are two other windows where there are efforts that look very, very promising. In fact, one of them, pulsar timing, is already collecting data. I won't talk about that now, but I'm happy to discuss it in questions if people are interested. But let me just mention this one in the middle, space-based interferometers. What you see here is a concept design for the LISA spacecraft. LISA stands for, I'm sorry, let me stay on this one. LISA stands for Laser Interferometer Space Antenna. And it's a mission of the European Space Agency that hopefully will fly in 2034. And what LISA will do is be sensitive to much lower frequency gravitational waves that would not be detectable on the surface of the Earth. So that will open up a new gravitational wave window where the sources are supermassive black holes. So we are pretty sure that supermassive black holes exist in almost every galaxy. You might remember the huge excitement when the Event Horizon Telescope produced an image of the gas around the supermassive black hole in a neighboring galaxy. But with LISA, what we will be able to detect is the collisions of those supermassive black holes far away in the universe. And one of the questions that we hope that might help us answer is frankly one of the biggest unsolved questions in all of science. Why do we think that 95% of our universe consists of dark matter and dark energy, which has very strange properties? So the next generation of astronomical telescopes using light will help us answer those questions, but we really hope that gravitational waves will have an important part to play in that story as well. So if you want to find out more about LIGO, there are many ways to do it. We have a website with lots of resources, scientific articles designed for a general audience, movies and animations. We also have a magazine that we publish regularly. You can also follow us on social media. You're most welcome to do that on Facebook or Twitter or Instagram. You might want to download that Chirp app that I talked about before. And indeed, you can also find out more about us on YouTube. We have a LIGO Virgo YouTube channel. And if you want to learn just a little more of the technical details of much that I've described, then we have a series of webinars on a playlist there that you might find interesting. And even more, if you do want to play around with the gravitational wave data for yourself, then you can find it at our Gravitational Wave Open Science Center. There are some Python-based tutorials and videos, and there are codes, and there's also people that can assist by answering questions that you might have. So please do engage with us. And let me just end by emphasizing what an exciting I was in China at the time of the first detection. And this inspired me what was happening The other people we went to the bar and came up with this notion of swirling around each other until they collide. So that was our way of marking just how important this new era of gravitational wave astronomy was. And I hope I've convinced you that it has a very bright future. And I look forward to answering any questions you have about this exciting new field. Thank you very much.
Right, well, Martin, thank you very much for this fascinating talk. I mean, you certainly presented not only the interesting history of the whole LIGO experiment, but you gave us a tremendous amount of evidence of what actually took place and why this discovery is important. However, I would like to start off with something of a controversial topic. Let's put it this way. When I was doing my basic research on the LIGO experiment, I noticed that one of the first results that is actually coming out as a result of my Google search is a New Scientist article from 2018 that puts under some scrutiny the findings of the LIGO experiment. So there was some talk around the Danish group that have submitted articles that are questioning the findings of LIGO. So if you could briefly summarize what is this main criticism all about, and how do you actually address those? Yep.
Sure, it's perfectly simple, I'm afraid. The Danish group have not analysed the data correctly. They made some incorrect assumptions, but to be fair to them, what they did start from was a diagram that we used in the very first detection paper that was not as clear as it should have been in the labelling of the diagram and the description of our methodology. So it was a perfectly reasonable question for them to ask. But I believe, and of course you need to look at our papers to make that judgment for yourself, that we have very clearly and successfully shown why their analysis was incorrect. Now, we did that in a paper that was published considerably later. So I do concede that it would have been better if we had produced that paper at the time of the New Scientist article, because hopefully it would have shut down the discussion much more quickly. In the end, because frankly, we were too busy detecting gravitational waves, finding the time to write a very long and detailed explanation of our data analysis methods, that took some time. But that paper now exists. I can send the link to your followers if they're interested in checking it out. And in fact, you'll find it quite prominently on the LIGO.org website anyway. So it's called A Guide to LIGO and Virgo Data Analysis. And it's very comprehensive. So it's written more as a piece of pedagogy rather than presenting new results. And we think that's also why so many people have enjoyed engaging with our Open Science Centre, because they want to try the analysis for themselves.
Right.
So, you know, of course, it was an interesting time. We felt that New Scientists were not representing the reality of the debate terribly fairly, but certainly, of course, they were trying to stir the controversy because it sells more magazines. Right. But in the end, I think the message of our later comprehensive analysis paper, well, let me just say that there has been no follow-up from the Danish group. So perhaps we've convinced them. I certainly hope so.
Right. So there is no controversy among scientists, at least. There is a consensus regarding the results.
Well, you know, let me emphasize they're a very respectable group of scientists. I'm not suggesting they were otherwise, but they were making certain assumptions about how we did the analysis that we subsequently challenged them on, and were able to demonstrate in the later paper that their analysis methods were not consistent with what we had done and were not fully correct. Moreover, because we released the data publicly, not immediately, but a few months later, everyone who has repeated the analysis independently of us using their own codes has been able to confirm the detections.
Right, right. So it's rather unfortunate that we still have, quite a lot of publications out there. Well, granted, not in scientific journals, but among the general public, there is still some conspiracy going on that this was, some sort of a fake discovery and that you guys made a mistake. So it's, sure. I don't know.
Well, I have spent 20 years giving public lectures on the theme of the moon landings and attempting to debunk those conspiracy theories. In the end, you just have to leave it to the people to judge for themselves. And, you know, we are too busy doing science to spend all of our time debunking those who say we are not doing science.
Right, right. Sort of a related question to that, because one of the claims being made there was that what you essentially detected was noise or something like that. So you touched on the during the presentation on this topic already, but if you can, you know, elaborate some more. How do we know that what you detected is not actually noise and that it is?
Sure. So there's a number of aspects to that. Again, my strongest advice to everyone is to go read that paper. But let me try to give you the highlights in a manner that's not so technical. So what we in astronomy very often do is we characterize our confidence in a detection in terms of a number of what we call sigma. So we talk about a 5 sigma detection being really, you know, nailed on. We are absolutely sure. So if you look at something like the detection of the Higgs boson, that was an example where the graph they produced, our particle physics colleagues, involved a feature that they estimated was 5 sigma away from what you would predict if it was just noise.
Right.
So the bigger the number of sigma, the more sure you are that it's real. Now, the problem for us fundamentally was, what is sigma? This is a quantity that characterizes the noise, and it's very hard to measure. So that's why we had to spend many months carrying out that analysis. So let me just try to briefly explain how we did it. We have a detector which is very sensitive to gravitational waves, but also sensitive to all of those sources of noise. But we have another detector as well. And one of the things that crucially helps convince us that we have a real detection is if we see the same pattern in both detectors at the same time.
Right, it's being replicated
at the same time because there's a small time delay. But in particular, what we could do is we could take the data from one of the LIGO detectors and artificially shift it in time by weeks or months or at least days. And then that means we can be absolutely sure if we line it up with the other detector and it looks like there's similar features, they cannot possibly be real because of the time shift. So this time sliding is what we did over the months after the actual detection to try to clarify how likely it was that something so similar was just a chance noise coincidence. And that was the aspect of the analysis by the other groups that was highlighted by New Scientist, where their approach to doing that was rather different. And I'm afraid that's why they reached the wrong conclusion.
Right, right. Well, I think that was a pretty straightforward explanation. I think it closes the door to all this controversy. So
I'm glad you asked because, as I said, we acknowledge if we had addressed those questions more quickly, then perhaps it would have closed the door earlier.
Yes, yes. Well, let's move to the physics department now. Most people are aware, the general public is aware, of course, that there are two main theories in physics. So first we have quantum mechanics, that is essentially dealing with very small stuff, and then we have the general theory of relativity, which is dealing with very large objects. Now these theories have proven to be extremely accurate in predicting events, but at the same time they sort of contradict each other. Now, will the discovery of gravitational waves actually help, physicists sort of unite these theories, or
That's a really great question. So let me try to give a comprehensive but a brief answer. The thing to begin to say is that general relativity is what we call a classical theory. So it's not quantized at all. And you're right, that's why there is this tension with quantum mechanics. So our predictions of the gravitational waveforms is coming from that classical theory where space-time is smooth. And frankly, the data that we are collecting right now is perfectly consistent with that. You do not display quantum phenomena because you are big. I am big. It's only when you go to the scale of electrons or protons or photons that these quantum effects become important. So in the same way, LIGO and Virgo are not directly probing scales where quantum gravity effects should be important. But you maybe remember I said there was that complicated slide with all the things about testing general relativity. And I said maybe we could chat about it briefly. Some of the tests that we are carrying out are related to aspects of quantum gravity. Let me just mention one. We think that photons, which are really fundamental in quantum physics, have no mass. They are massless particles. But if the photon has a counterpart in gravitational waves, that is like the quantum analog of the photon, well, we call that the graviton. And maybe the graviton could have mass. And if it did, that would be a really big deal, because it would argue that unifying quantum theory and general relativity is maybe not so straightforward.
Right.
I mean, it's not straightforward anyway, but it would suggest it was even harder if the graviton had mass. So we are able to look for evidence of that in our signals, because we can conduct kind of simplified treatments of what a massive graviton would look like in terms of the gravitational waveforms. And we don't see signs of that. So everything so far points to that prediction of general relativity translating neatly to the quantum world, that gravitons, just like photons, are massless. Now, there are many other examples like that where we're just starting to chip away at the key questions that will help guide us to a theory of quantum gravity, but we have a long way to go.
Right, and is there an experiment in mind that is to be made in order to, prove that gravitons actually don't have a mass? Because right now you're extrapolating, sort of.
Well, we are, but again, we're extrapolating on fairly solid ground. Right. I think if you're looking to use a gravitational wave experiment like ours, then what one is doing is generally looking for indirect evidence. So let me try and explain. I mentioned briefly how we can use gravitational waves to measure the expansion rate of the universe. Now, there's a whole range of quantum gravity models that predict a certain behavior for the expansion rate of the universe. So it's not so much that we would use gravitational waves to, like, detect a graviton or isolate it in our detectors. It's that we would explore predictions of theories in which there is a graviton with certain properties and try to decide if the data are consistent with those or consistent with another.
Right.
So another version of that is theories in which there are extra dimensions, which isn't really directly to do with quantum gravity, but it is related, because one of the ways that people have proposed that we might unify general relativity with quantum gravity would be via something called string theory. But the weird thing about string theory is that it seems to work best in universes with extra dimensions. So we can imagine using gravitational wave detections like I've described to try to constrain whether those extra dimensions exist. In fact, one of my last papers that just got accepted is looking at how LISA, the spaceboard detector, might just be able to say something about the existence or otherwise of those extra dimensions. So that means it's relating a little bit to string theory as a possible route to quantum gravity.
Right. Right. Okay. Now, moving to another very important theory of science, or sort of a law in science. This is the law of thermodynamics. Now, there's a famous saying in physics that if your theory contradicts the second law of thermodynamics, you should throw it in the trash. Now, my question is more general here. And it's related again to the general theory of relativity, which seems to be sort of contradicting the second law of thermodynamics. Now, can you address this question?
Well, I can, but I would challenge your basic premise. In what way do you see general relativity as challenging the second law of thermodynamics? I'm puzzled why you would think that.
Well, I'm puzzled why this question is being asked. To be honest, I would assume that there are good reasons for that.
Let me anticipate why people are maybe asking it. It's often to do with the expansion of the universe, and it's often to do with the fact that somehow that makes people think that that's a violation of thermodynamics because, well, where does that energy go as the universe expands? And the fundamental flaw in that way of thinking is a very subtle one. So, I sympathize with that view. This is complicated stuff, but it's basically a very deep principle in physics as well, which is that conservation laws are related to symmetry properties. So when we think of some property as being conserved, like momentum, that's because if you imagine a little experiment where something collides with one other thing, the symmetry is supposed to say that you could run the clock the other way and it would still look the same. Now, that isn't the case for the universe. There's a fundamental breaking of that symmetry because there's a direction of time associated with the expansion of the universe. So in actual fact, I get this, lots of emails about this, and usually it must be very frustrating for the person who sends the email, because I say, well, on the first line of your email, you say the universe should satisfy energy conservation. And then I say, well, why? Why are you saying that? If the time symmetry is not built in to our cosmological model of the universe, then that means that the notion of energy conservation needs to be handled much more carefully. So I'm kind of dancing around an answer, but let me just say that I can certainly send you some links to some excellent popular articles that discuss this in greater depth, and maybe your followers will enjoy reading those.
Yes, I think that would be useful, so we can follow up on this on this question. Now, you did mention conservation of energy, and we have a question here regarding the bodies that emit gravitational waves. Now, when they emit gravitational waves, do they actually lose any mass? Now, you did mention that gravitons, according to theory, don't have a mass. So how do you respond to that?
So let me give you the Einstein general relativity answer. If gravitons have mass, then that would be a different situation. If gravitons are massless, then no, the rest mass of the body is unaffected. That means the mass that it has if you were in a reference frame that was following along, traveling along with the massive body, like a neutron star or a black hole. But there is radiation carried away from the system. That's basically why they spiral in towards each other. It's because they're losing that gravitational wave energy. So it doesn't mean that they lose mass as such. There is another way to look on it, however, if we do want to reintroduce quantum notions, which is that black holes can lose mass through what we call Hawking radiation. But again, that's not relevant for the kinds of events that we're detecting. But who knows, maybe in the future, we will have the capability to detect gravitational waves from events which are also radiating Hawking radiation. And then, that would add an additional way to test whether those ideas about Hawking radiation are correct.
Right. Okay, a question here about how do gravitational waves actually interact with big, massive bodies.
Sure.
Do bodies like that, or black holes, or large celestial bodies, do they actually slow them down? How do they have any effect whatsoever?
That's a terrific question. Largely, the short answer is no, but it requires unpacking a little, because there's a more subtle version, which is maybe. In theory, yes, but the point is, well, if we think back right to the beginning of my talk, I was emphasizing how sensitive LIGO has to be to detect anything.
Right.
And that's because space-time is incredibly stiff. That might sound a weird thing to say, but what I'm meaning is, even if you have something as violent as two black holes orbiting each other, that shakes up space-time by an incredibly tiny amount. It's like, if I jump on a trampoline, the trampoline moves a great deal, but if I jump on a block of concrete, the concrete hardly moves at all. The concrete is much more stiff. So space-time in those terms is, 10 to the power 100 or so stiffer than concrete. Now, what that means is that if we want to imagine that a passing gravitational wave might disturb a massive body, then, or also that the massive body might disturb the gravitational wave, a kind of mutual interaction, then that massive body needs to be curving space-time a great deal. So the bottom line is, if you have gravitational waves produced by two black holes, and if those waves, as they travel towards us, happen to pass close to a very dense object, like another black hole, then those gravitational waves could be affected. They could be lensed. We have a phenomenon called gravitational lensing, which we see in light. And actually, it could happen for gravitational waves too. We're already searching for it, but we just haven't found any definite examples of gravitational lensing. So the short answer is yes, gravitational waves and matter can interact, but because space-time is so unbelievably stiff, the only concentrations of matter that would be able to affect a passing gravitational wave are essentially like black holes themselves. They've got to be incredibly dense and compact.
Right. Now, we do know that all bodies that have velocity, I don't know if I'm phrasing this right, that all bodies that have velocity essentially emit gravitational waves. Now, having said that, I'm assuming that while I'm moving, I'm also creating gravitational waves. Will that be a correct assumption?
That's correct.
Yeah. Is there a way to actually capture those and see them?
No. Sometimes I include a slide on that. Maybe I should have this time. One can do a calculation along the following lines. You can imagine having two 1,000-kilogram masses, like 1 ton, orbiting each other in a laboratory. You know, put them on a turntable and have them spinning around each other. Let's say they were spinning around each other 1,000 times per second. You know, I haven't done the sums, but that would require a lot of power, and I wouldn't want to be too close by in case it flies apart. But you can calculate the gravitational waves produced by such a spinning pair of masses, and it's unbelievably tiny. I mean, the number I quoted for two black holes merging was incredibly small. Remember, 1 millionth the width of a human hair? The signal produced, if we tried to do it in the lab, would be about 10 to the 20 times smaller. So we really have no chance of being able to build a gravitational wave detector. And again, it's because space-time is so unbelievably stiff. So in principle, when I wave my fist, I'm producing gravitational waves, but we couldn't ever hope to measure them. We have to rely on the universe to be our cosmic laboratory to produce these signals.
And even theoretically, we will never be able to create a machine that spins so quickly that we...
I'd love to think so, but I can't imagine how. It's always dangerous in physics to say we can never do something, but there's a very interesting brief lesson from history. James Clerk Maxwell, in the middle of the 19th century, demonstrated the existence of electromagnetic waves, and those are produced when you have changing electric and magnetic fields. What do I mean? Well, two electrons whizzing up and down a radio wire, that's how radio signals are produced. It was only 30 years or so between James Clerk Maxwell predicting theoretically that such waves exist until we were able to produce them ourselves in the lab. We've no prospect of being able to do that with gravitational waves. If we could, and I emphasize a big if, then it would open the door to anti-gravity devices and hoverboards and all of the things we see in sci-fi.
Right. We have like tens of questions being submitted right now, so I'm gonna have to take a few seconds just to pick one. So, for example, I think you briefly touched on that, but how do you synchronize the time between the sites so you can determine the position of the event?
Well, actually, it's tied to the GPS system. So the instruments are operating with very, very accurate atomic clocks that allow us to determine very, very precisely when a signal arrived at one site and when it arrived at another. But remember, they are 3,000 kilometers apart, even the LIGO ones, and Virgo is further apart. So the time delay is actually milliseconds, and that means we can measure that really quite precisely.
Right. Okay. Can you share a little bit more about the pulsar timing arrays?
Yeah. Actually, that leads on directly from what I just said, because the idea of a pulsar timing array is not to use atomic clocks in our labs, but to use pulsars, spinning neutron stars, like clocks out there in the cosmos. When a gravitational wave passes by, it does affect the rate at which time flows. That's one of the consequences of general relativity. So if a gravitational wave that's emitted deep in the universe is spreading out through the cosmos, when it reaches our galaxy, those gravitational waves will pass by pulsars in our galaxy, and that will affect the arrival time of radio pulses from those pulsars. So if we can somehow reconstruct from that information where the gravitational waves came from, you've got yourself a galactic scale gravitational wave detector. So the principle's not so different from LIGO, but you're using pulsars rather than laser beams in our vacuum tubes. So there's no detection yet, but there's a paper just appeared a few months ago where I don't work in that collaboration, but I talk to them a lot, and we share a lot of activities in terms of education and outreach. And they've analyzed 12.5 years of data, and they have just the hint of a possible signal. So we just need to wait a little longer, but it could be that they will have detected something as well.
Right. Okay, a question here about gamma rays, actually.
Yeah.
So why did gravitational waves arrive earlier than
Well, that's
gamma rays?
an excellent question. According to general relativity, gamma rays and gravitational waves should both travel at the speed of light.
Right.
So we think the reason why they arrived 1.7 seconds later is that they were emitted 1.7 seconds later. The gravitational waves came from the very heart of the merger, where the two neutron stars were right on top of each other. But then that produced a kind of shock wave, if you like, which resulted in the gamma ray flash from further out in that pair of objects, you know, the surrounding gas and material. And therefore, it's quite consistent with our theory, our theoretical expectations, that the gamma rays should arrive a little bit later. But of course, we can kind of test that a bit. We can say, well, let's suppose that the gamma rays did get emitted at exactly the same time. Because these neutron stars were 130 million light years away, that at least tells us the following. It says that even if they were emitted at the same time, the speed of gravity and the speed of the gamma rays can only differ by a tiny, tiny amount, since they only lagged behind by 1.7 seconds. So that's kind of thinking about it not from the theoretical perspective, but just purely taking the data and saying, let's not assume Einstein was right. Let's see what we can say about the time of arrival and the speed of gravity. And therefore, you know, I am pretty confident that the prediction that gravitational waves travel at the speed of light is a very solid one.
Okay. Okay, a question related to the other projects that are currently going on besides the LIGO experiment. Now, within LIGO, you are working with two pretty similar interferometers.
Yeah.
Now, how are you going to align the data with the other experiments that are being conducted?
Well,
is there a difference in the equipment that is being used or in the principles that are being applied?
There are some differences, but none that are showstoppers. So we've already had 3 years of operating with Virgo in their advanced configuration. Remember, they began in 2017. So Virgo was not operating when the first detection was made in 2015, but actually our Virgo colleagues were already contributing to the data analysis. So the data analysis methodology is set up to allow for detectors of different sizes and different sensitivities in different parts of the world. But it just is better if they can be as similar as possible. So that's why it's very promising and very exciting that the two LIGO detectors in the late 2020s will have a third almost identical twin or triplet. So Virgo will be similar, but not exactly the same. But LIGO India really will be almost identical to the two LIGO detectors, and that will make the data analysis a little easier because we are so confident that they're operating in the same way.
Right. And now, regarding the Japanese experiment, what puzzles me is that it's being built in Japan. I mean, it's we're talking earthquakes here. So how do you how are you guys going to resolve that?
Well, bear in mind that if you're trying to no, it's a great question, but bear in mind that if you're trying to detect changes in the curvature at the level of 1 millionth the width of a human hair, then you're not just talking earthquakes that would be a problem. You're also talking someone, you know, with heavy footfall in the corridor close to the lab. So what all of the detectors have had to develop is incredibly effective seismic isolation capability. So I was going quite late. I was conscious there was a lot to cover. But when I mentioned the Glasgow work replacing the steel wires with silica fibers, that's really one of the chief advantages of that approach. It makes the mirror more isolated from its environment. Now, you know, if it was a major earthquake, obviously the lab would not operate because there would be other things to consider, like people's safety. But, you know, the ability to isolate the systems from that seismic noise means that actually, you know, Japan wasn't so much different from the Pacific Northwest or, you know, other locations. And the big advantage of CAGRA is that there's an underground mine. So isolating from some of the effects of gravity, what we call gravity gradient noise, is made easier if you build the detector underground. So that's why CAGRA was a very viable partner. LIGO and Virgo are on the surface, but CAGRA's underground. So what they maybe lose in terms of their seismic quietness, they gain in terms of being underground.
Right. Do gravitational waves decay?
Well, that's a great question too. And if I look at some of the things I briefly touched on before, I didn't go into details, of course, but I said there was a whole barrage of tests that we've carried out to test general relativity. One of them is effectively a test of whether gravitational waves decay. It's looking for what's called a dispersion relation, which is something you would get if you have a wave that decays. So for example, when a radio wave is like absorbed by some other medium, then there's a way to understand how the electromagnetic waves decay as the wave penetrates that body. So we are looking for that effect, but to all intents and purposes, gravitational waves do not decay. And it's really just back to that question of the stiffness of space-time. You know, so I guess the more complete answer is to say that yes, in principle they do, but you would need to be considering them passing through a medium of such unbelievably high density that, you know, as they travel just through the normal universe or through a planet or through a human being, then, you know, they really don't decay at all.
So if you have to make a thought experiment, what would an object like that be like?
It would basically be like a black hole or a neutron star.
A black
hole. In fact, there's some great sci-fi about this. There's a guy called Robert Forward who was a pioneer in this field. I never got to meet him, but some of my LIGO colleagues know him well, the ones who were awarded the Nobel Prize from the previous generation. And he's written some sci-fi novels about an alien civilization that exists on the surface of a neutron star. And I think they communicate using gravitational waves, if I remember rightly. So they were able to manipulate the waves because they are living in such an intense gravity environment.
Living on a neutron star? Is that even theoretically possible?
Well, you know, read the sci-fi. I mean, a lot of sci-fi is far beyond what we think is theoretically possible, but it's always dangerous to say never. Let's just say that the aliens didn't look anything like us.
All right, here's a side question for you. You as an astrophysicist, who's your favorite sci-fi author then?
Oh, that's a great question. It's very hard to give a single answer, but I will try. I think just in terms of the scientific ideas, my favorite is probably Arthur C. Clarke. I mean, he's not the best writer, to be honest, but the quality of the ideas and the richness of the detail that he goes into, I really have always enjoyed. I mean, it's one of the things that inspired me as a kid, was reading Arthur C. Clarke's stories, and then, of course, now having the chance to actually do some of the things that he talked about.
Wasn't it said about Arthur C. Clarke that he was the best physicist among authors, and Asimov was the best author among physicists?
That's a very neat description. I wasn't aware of that quote, but I think that sums it up very well.
Yeah.
Asimov was a much better writer,
right?
Clarke's physics was really great and very intriguing and inspiring for for a youngster.
I personally prefer Asimov, maybe exactly because I'm not doing astrophysics. So
yeah. Now the modern heir to Arthur C. Clarke is someone called Stephen Baxter. So let me just cheat a little and give him a special mention too.
Yeah, go ahead.
Because his ideas are also fascinating. I think he's a better writer, but I just haven't had the time to read so many of his books. Lots of people keep telling me, read Stephen Baxter, you'll love it.
Okay, Stephen Baxter. Okay, we're gonna check this out.
Check him out.
All right. Okay. Promise. Okay. So let's speak about the future now. Now, what do we expect? This new discovery of gravitational waves and the more data we accumulate. What are some insights about the universe that we are expecting to uncover and to find out?
Great question. So let me just highlight briefly a few, and then we can see if you want to dig into them a little deeper. So one is to do with the astrophysics of the sources themselves. So neutron stars, when they merge, we showed the little cartoon of them spiraling around and then they merged. As they are doing that, they are distorting each other. So the neutron stars are no longer perfect spheres, they are tidally distorted. And the amount by which they are tidally distorted will change the gravitational wave pattern. So we don't yet really have much detail in that because our data haven't been good enough. Yet we know that neutron stars merge, but what we want to be able to do is to study the detail of that merger sufficiently that we can really work out what the inside of a neutron star is like, what it's made of, you know, how dense it is, what the pressure is. So that's one of the big frontiers, is understanding the astrophysics of neutron stars. Another is understanding the astrophysics of how black holes form. So that's not so much from individual events, that's from looking at the population, from seeing, oh yeah, we have so many of this mass and so many of that mass and so many of that mass. So that's telling us probably how those black holes were formed. Did they build up in one step, or did they build up like a hierarchy? You go from small black holes to medium size to bigger and bigger. So those are the kind of questions that we hope to answer when we have hundreds of sources. And then the third example is in the area of cosmology. So it's what I alluded to in one of the final slides, that there are these big unanswered questions about dark matter and dark energy. Now, I personally don't think that gravitational wave sources like black holes have anything directly to do with dark matter and dark energy. But what they can help us do is probe dark matter and dark energy, because the presence of dark matter between us and a gravitational wave source will affect how that signal travels towards us. Because it's kind of the same as what we do with light when we look at distant exploding stars called supernovae. There was another Nobel Prize for that, awarded in 2011, which was to do with the realization that our universe isn't just expanding, it's speeding up.
Yeah.
And we hope that with gravitational wave sources, we can help to probe that in greater detail. How fast is it speeding up? Has it always been speeding up, or did it first of all slow down and then speed up? Those kind of questions, gravitational waves could help, because we expect to see them very, very far away, further away than we can see those exploding supernovae.
Now, which one of
3 areas? For starters.
So which one of these questions do you find you personally more fascinating? I mean,
well, I'm going to cheat again and say that I find them all fascinating, but the one that I work in is the third one.
Yeah.
And the one that I'm most involved in is trying to use gravitational wave sources to measure the expansion history of the universe. So far, we've only been able to do that nearby, but the further and further away we can do it, then the further back in time we'll be looking, and therefore we can answer these questions about, has the universe always been speeding up, or did it first of all slow down and then speed up? And if so, what does that tell us about dark energy? That's the main focus for me for the next 20 years.
Right. Okay, now we are seeing that LIGO is certainly, and the discovery of gravitational waves is certainly part of this whole sort of expansion of fundamental science. Now we are seeing discoveries being made daily. Well, not daily, but very, very often. We can barely cover them. But there is an argument out there that you know, if I have to phrase it this way, if you go inside a regular apartment in the 1950s, and if you go in a regular apartment now, if you remove the screens, there is nothing fundamentally different. So there is sort of you know, a general opinion or a theory there, or a discussion there, that there is a stagnation in applied science and in what we are doing with the new knowledge that we accumulate. Now, do you find this to be a truthful observation? Do you think that there is a stagnation in physics?
No, not at all.
Not at all.
Absolutely not. I would challenge anyone that says that to just look at the impact of the pandemic in the last year, and to imagine how different the experience of lockdown would have been if it had happened in the 1980s or 1990s.
Right.
Just imagine with dial-up internet having a conversation like this one.
Yeah.
So that's just one example. I mean, that's not why I do fundamental physics, but it's certainly one of the useful payoffs. And anyone that says that now we should just do biomedical science, of course they have a good case, because there are many challenges to be overcome in understanding the nature of viruses and to prepare for the next pandemic. But I would argue that we need to keep doing the fundamental science as well, because that's what will insulate us from the full impact of the next global catastrophe. In just the way, perhaps unexpectedly, we have come to rely so much on that IT infrastructure to get us through aspects of the current pandemic.
Yeah. Okay, that was a great answer. So you, as an astrophysicist, is there a question, outside of the ones that we just discussed, a question that doesn't allow you to sleep at night? I mean, what is it that troubles your mind as a physicist?
That's a great question. Well, I mean, if I just restrict myself first of all to physics, then I think the one that I still sleep pretty soundly, but I am fascinated by it all the same, and sometimes it does just make my head throb, is kind of just quite fundamental. It's the fact that why should there be a universe at all? Because I mentioned that we've got this string theory landscape, as one of the possible ways that you can unify gravity and general relativity and quantum physics. But string theory doesn't just give us like one, gift wrap universe with exactly the right properties. It seems to give us 10 to the 500 different possibilities. So what's so special about ours? Why did our universe emerge from all of that and not a very different kind? I'm not quite sure what to make of that. I don't know whether it's even a well-posed science question or just something to keep you awake at night or something to chat in the bar over a beer. But that's certainly one that it isn't directly related to my own research, but I'm fascinated by it.
Right. Okay. So now that we are closing our discussion, briefly, what's next? What's next for LIGO?
Well, in the immediate term, our task is to complete the upgrades to be ready for our 4th observing run. That's challenging because everything is challenging within COVID, but we believe that we're on course to be ready sometime, maybe around middle of 2022. And I should have included this slide because you saw the slide where the number of detections was rising sharply. Well, if all goes to plan, it's going to rise again. So we'll be looking at perhaps many hundreds, even 1,000 detections. So what that's going to help with is some of those population level questions. So yeah, that's the short answer. What's next is getting ready for observing run 4. And we've got about 18 months to do it, but there's a lot to do.
Yeah, upgrades. Well, that sounds great, Martin. I want to thank you very much first for the presentation and for this fascinating conversation that we just had. Thank you very much for putting in the time to talk with us. It's really has been a privilege. I wish you all the success to you and your team and everyone involved in this. I mean, you guys are uncovering the mysteries of the universe. I mean, it's if you are not defined as essential workers, I don't know who is. So I really hope that everything will go smoothly and that we will be hearing more about LIGO and you personally in the future as well.
Thank you very much. That's really kind of you. And I've really enjoyed it. And thanks to everyone who submitted questions. It's been a real pleasure.
All right, very good. I will ask you just to just stick around for a couple of more minutes before closing in. I have a few more words to say to our viewers, and then we're gonna briefly chat and say goodbye. But thank you for now, Martin. Okay, so ladies and gentlemen, moving forward, as you know, every time that we do a close up, I'm gonna briefly show you what is coming up next. So if I can ask the guys from the engineering room, is that how you call it in English, to please show the next events that are coming in. First of all, of course, I would like to thank the National Culture Fund of Bulgaria. Your support is essential for making us able to actually produce this show and to continue our effort in popularizing science. So thanks very much to the support of the National Culture Fund of Bulgaria. The next event that we are going to be doing is it's on the topic of, how do you pronounce that? Bacteriophages, I think, is the right pronunciation of the word. Bacteriophagi in Bulgarian. So on 2nd of February 2021, we will be talking about these tiny little creatures and the possibilities that they present in terms of future therapies that are to be developed. Then we will have another physics presentation. We will be tuning in to the radio universe on the 16th of February live stream at 8 o'clock. The event will also be in English, so for whoever is watching right now from outside Bulgaria, please you can join us and enjoy this event as well. 16th of February. 8 o'clock from here. Again, you can listen to our podcasts. They're all in Bulgarian so far. But if you guys are enjoying podcasts, we have 3 different formats that we're currently working on. So subscribe and listen for some great science conversations. Thanks a lot to our supporters from Patreon. If you would like to support us, guys, you can go to patreon.com/ratiobg. And help us out continue popularizing science. Check out our website, subscribe to our YouTube channel so you can receive all the notifications when we go live. Thank you for watching us tonight, and I will see you next week. Thank you. And